Hello everyone. I am Mythra Balakuntala from Collaborative Robotics Lab at Purdue University, and my advisor is Dr. Richard Watts. And my talk today is on coaching by demonstration for learning contact-rich tasks for robots. So here is a brief outline of the talk. First, I'll go over what is coaching and how is it different from traditional imitation learning. Following this is the list of contributions of our work and how we are going about the methods, and finally the future work we are proposing. So what is learning from demonstration? So traditionally robots had to be programmed to perform any new task, but with the rapid introduction of collaborative robots and lead through teaching, new paradigms have been established, such as programming by demonstration or imitation learning. So basically these methods try to use users demonstration or human demonstrations to teach the robots different tasks. There have been different methods which have been proposed for imitation learning in the last 2 decades. Early methods included things like dynamic motion primitives, which are based on which are similar to something like PID control with forcing functions. They're still popular because of their scalability. There are also new state-of-the-art methods using deep learning, such as LSTM, or using deep reinforcement learning methods such as soft character critique, where basically using those you can learn to imitate user demonstrations. But these methods have various issues, such as requiring either impractical number of demonstrations if you want to implement it for like a physical task, or they don't generalize well to contact-rich tasks. But the primary gap in across all these methods is the lack of focus on improving task performance. Basically, imitation is aiming at improving task success, or basically achieving task success, rather than improving task performance. This is analogous to like how humans learn. For example, a 9-month-old baby starts learning motor control skills just by imitating an adult. But it is not until they are 3 or 4 they start to incorporate external feedback to efficiently learn tasks. So research has shown significance of external feedback in improved learning and also improved quality of task execution. So what exactly is coaching? So coaching is this process of providing specific feedback for efficiently improving task performance. This is what we are referring to as coaching. For example, a kid can learn to shoot a basketball by looking at others who are playing with him. But to achieve world-class performance, all athletes require coaches. This is because coaching provides specific directed feedback on exactly what to modify to maximize the overall performance. However, coaching methods in literature either use human feedback as just a continuous evaluation or reward function, or they also use it as bias to trajectory alone, which is just changing like a position of the robot. This is not really practical, or they don't generalize well specifically to like contact-rich tasks. And most of everyday tasks where we want to implement a robot has some kind of contact, and just modifying a trajectory will not suffice. So given the significance of coaching and the lack of using directed feedback for improving, what exactly are we proposing? So these are the two main contributions of our work. We have created a framework that enables learning complex the contact-rich tasks just from one single visual demonstration. So this is exactly like how humans show each other. You just demonstrate it using a visual demonstration, and also sporadic feedback from the coach. So this framework eliminates the need for large number of demonstrations as well as continuous feedback from the humans. Additionally, in our framework, the tasks are broken down into a sequence of subtasks, or what we call as skills. And these skills are run through skill translation and practice. So the skill learning uses a novel state representation network which we created, which basically combines data from different sensor modalities such as image, force torque, tactile sensors, as well as position encoders of the robot. And we showed that using such a state representation improves the task learning performance. Now that we know why coaching is necessary and what exactly are we doing, or what is our contributions, we'll go into the details of how we are doing it. So here is a brief overview of our entire coaching by demonstration framework. So the input framework is an RGBD video, which is basically collected using a 3D camera. And the demonstration is segmented into a sequence of subtasks, or what we call as a priori skills, whose goals are inferred from the video itself. So first, the robot uses a reinforcement learning to tune the skill policies of each of these skills to match the demonstrated performance. And since we're using just one demonstration of the entire task, this is kind of like a one-shot learning where you're learning from just one example. So the second part of this online learning process is the coaching itself. So the coaching feedback is provided sporadically to optimize the global performance. So the feedback is not really labeled and it's not like a complete demonstration. Thereby, learning from coaching is akin to a zero-shot learning work. The skills in our framework are mapped to the closest skill the robot already knows. We'll come into how to learn unknown skills next, but basically the skills are mapped to the closest skill which the robot already knows. And the one-shot learning is basically retraining these skills from starting from a known skill. And for example, if the robot has to learn how to clean a table, writing or, for example, peeling are similar skills which also involve similar kind of contact, and the robot can basically use the policy for that scale and retrain starting from there. So first is the part of skill segmentation and how do we learn new unknown skills. So basically the task is segmented into skills using what we refer to as physical interaction key points. So these are frames in the video where two objects interact or there is a change in interaction condition, either between two objects or between hand and an object. And these segments are mapped to the closest skill, which the robot already knows. So we use basically the interaction key points to segment the entire video into sequence of sub videos. And from these videos, we infer details regarding relative velocity between objects, relative positions, and object poses as features. And we use these features to classify each segment into a known skill. So how about what do we do when we have to learn new unknown skills? So the new unknown skills are learned using a novel skill learning framework as shown here. So we use like an end-to-end framework to learn these skills from few human demonstrations. So both the reward and action space are inferred from the demonstrations in this framework. So it eliminates any requirement of hand defining rewards or action space for the um, learning the skills. Details of these is present in our upcoming paper. I'll discuss some of the details here. So specifically for the skill policy learning, we can use any deep reinforcement learning methods such as soft actor critic, where both the action space and the reward are learned from the demonstration. So what we do is for the action space specifically, we look at users' action directions in the demonstration where there was contact, in which directions there was contact, and which direction had position changes. And based on that, we define an action space for the robot. So it's basically a union of force action space and the position action space. And that's how we define action space basically from a set of demonstrations. And for the reward itself, instead of actually hand generating a reward, what we do is we infer goal states from the demonstration. So since we already segmented the skill using physical interaction key points, so these key points indicate where is the start or end of a skill. So usually at the start of the skill, the states are still not successful. And towards the end of the skill, it's like success state. So what we do is we infer a bunch of positive and negative examples of successful goal states from the demonstration and train a classifier to form the reward function for our skill. In addition to the learning the reward from the demonstration, we also proposed a multimodal state representation, which improved the overall learning performance. So the representation combines information from both color as well as depth images, in addition to the force torque, tactile values, and position values from the robot. So the color and depth images are passed through convolutional networks and fully connected networks. And finally, all the features are combined using a fully connected network to form 4 decision variables. The first of which is the contact condition. So whether there was a contact in the skill or it is just a trajectory skill. And the second one is what type of contact occurred in the skill, which is basically, was it like a position contact, or was it like a line contact, or was it a surface contact? The third one is whether it was a tactile contact in the sense, for example, a difference between grasping an object from side to side versus actually touching a table. So a tactile contact would just be only a contact with the hand. And finally, the last decision is an important one on occlusion. So this is necessary because the reward classifier is basically using images to generate a reward. So if the robot is actually occluding the scene, we should not be providing a reward to the robot based on the image, because the robot cannot make a decision since the image has occlusion. So the decision whether there was occlusion or not is a significant one. So this entire network is trained in a self-supervised manner, so it doesn't need any human labels. It is done using a combination of heuristic and a random policy, which generates different types of contact, and robot uses that to learn the parameters of the network. So the next part of uh, the entire framework was the one-shot and zero-shot segments of self-evaluation and practice. The self-evaluation is basically uses a similar framework as the skill learning, where you start from a closest skill the robot already knows, and you retrain starting from there. The learning follows the similar procedure, and the action space and the reward are inferred from the demonstration. And the goal of self-evaluation is to basically match the demonstrated goal image state, which is seen in the demonstration itself. On the other hand, coaching feedback is used to modify the entire action space by adding constraints or to provide a sporadic reward to indicate that the robot is doing well. So the self-evaluation is akin to reaching a local minima kind of, and after some iterations, the performance plateaus, whereas coaching feedback is usually used to move the robot out of a local minima or push it towards like a global minima if you see saturation in performance. So here is an example of how we do coaching in our task in our framework. So this task is basically a material transfer task where the robot has to scoop and unscoop a given amount of material. And in our case, for this, we basically use text-based input for the coaching. And the input was basically like constrain your motion to just tipping actions when you're unscooping, or focus on unscooping using tipping action. And basically what the robot learned at the end of this is a relation association between the amount of material the robot currently has, and after it tips for different angles and different durations of time, how much is the material left in the robot's hand. So basically the robot learned how to scoop a different amount of material. So here are some results based on our framework. The first is the results for the skill learning framework itself. And as we see, the skill learning framework achieves an average performance of 93%, which is significantly higher than just using like a modeled controller or using naive RL methods where you can kind of formulate a hand-shaped reward and just use RL for learning. The second table shows the overall performance of the overall framework in learning some tasks like scoping, cleaning, and writing. So in this case, it's basically the learning time in iterations with respect to the maximum. And we compared it to our own framework without coaching, where we just did like self-evaluation. And also we compared it to state-of-the-art deep learning methods for just imitation learning. So as we see, the coaching by demonstration framework achieves the performance in like a fraction of time compared to like the best methods, or converges in a fraction of time. Again, similar to this, our main focus was on the task performance itself in terms of accuracy. So basically, we defined task performance as how close the robot was with respect to the human performance. And we compared it against the demonstrated task. And we did the same comparison for the three different methods, the coaching by demonstration framework we proposed without coaching, as well as just imitation learning using demonstrations. And as we see, even here, our framework performs significantly better than state-of-the-art methods, as well as like without coaching. So which shows the significance of using coaching. Here is a video of the skill learning itself. So here we provided like 20 demonstrations to learn an unknown skill of writing. And the goal was to write a character. And as you see, the robot kind of infers both the position and action space. That in XY, it's like a position translation. And in the Z direction, it needs to just achieve contact and apply a certain force. Again, a similar skill is the cleaning task, where the robot was supposed to clean a region of interest. And initially, the robot started out with random actions. And as you see, after 6 hours, the robot is able to achieve a very good performance. And finally, another task which I evaluated was peeling a vegetable. Here, the goal was to just do one peel along the vegetable, not to peel the entire one. And we showed that the robot can learn how to peel like one side of a vegetable within like 2 hours. And we also were able to apply the same work to different applications. So we are also venturing into other applications such as telesurgery, where we are implementing the similar framework for tasks such as cricothyroidotomy, which is basically performing an emergency procedure to intubate a neck to form a different airway. The other task we are trying is also called debridement, which is basically removing dead skin off the surface of a wound, and peg transfer, which is basically a training procedure for laparoscopy. So what you see in the videos are basically on the left is something called the palpation, which is the initial step for the cricothyroidotomy task, which is to feel the neck and identify features on the neck on where to do an incision. On the right, what you see is basically doing the incision after you know exactly where to do the cut. So both of these task skills were again learned using the same skill learning framework, which were demonstrated by humans. And finally, these initial results which we have showed significant promise on why coaching is important, and we are extending it in a few different directions. The first one is we are proposing a coaching interface study because we are developing two new coaching interfaces in addition to the text-based input, which is speech and as well as gesture. So related to this is we are trying to create a mapping function, which is mapping this non-symbolic gesture or speech coach inputs to constraints on the action space. So basically creating this mapping function. And third, we are trying to also create a new framework for transfer learning across similar tasks. So given a task, and how do you basically map on if you have already know some other tasks. And finally, we are proposing a transfer learning to improve tasks. Finally, we are proposing what we call as reverse coaching, which is basically if the robot already has data from expert demonstrations on how to successfully do a task, and it is collaborating or a new user is teleoperating it, the robot can provide guidance to the user on how to exactly like follow a successful trajectory. So it's something called reverse coaching is what we are trying. These are our list of publications, and that is the end of the talk. Thank you.